This chapter is about support vector machines.
Before we study SVM, let's talk about linear classifier first. Linear classifier is a classifier which can be represented as a line. So this is the form of linear classifier. So this is straight line, this is slope, right? So if for a new data x, it's if the function value is above this line, then class value is red, and the function value is below this line, then its class value is red. Okay, so something like this. So this is the definition of linear classifier. We have seen linear classifier before when we study neural net. Okay, the perceptron was linear classifier, and there are a couple of more linear classifier in machine learning, and naive Bayes and logistic regressions are also known as linear classifier. But there are some controversy around this issue, whether these two algorithms are linear classifier or not. Because in naive Bayes' case, naive Bayes is linear only when it is represented in logit form, logit, and in logistic regression case, it is linear only if it is represented in logistic function form. Okay, so a little controversy there, but many people say these are linear classifier as well. Okay, so you can say naive Bayes and logistic regression is kind of linear classifier in a twisted form. Okay. So anyhow, we don't use linear classifier often today because linear classifier is too simple. Okay, and almost every real-world problem is non-linear. So it is almost impossible to solve a non-linear problem using linear classifier, right? That's why we don't use linear classifier anymore. So that's the problem of linear classifier. Okay. So in this chapter, we study SVM, and SVM is one of the state-of-the-art classifier. So up until the deep learning comes along around 2010 something, this SVM was the most powerful algorithm, and it is still very competitive. Okay, very impressive algorithm. Okay, and what is very interesting is SVM. One of the state-of-the-art algorithm is linear classifier. Okay, so yeah, it's very interesting. Okay, one of the most powerful algorithm is linear classifier. So this algorithm is very interesting algorithm. Okay, we're gonna study this SVM in this chapter.
So as I said in a previous slide, linear classifier can be represented as a linear line. So this one here is an example of linear classifier. But almost every real-world problem is non-linear problem. So this is an example of non-linear problem. So obviously, we cannot solve this non-linear problem using linear line like this, right? So because of that, most machine learning algorithms are non-linear classifiers. Okay, but what is very interesting in SVM is SVM is a linear classifier, but it still is very competitive with other state-of-the-art machine learning algorithms. So that's what makes this SVM algorithm very interesting. And finally, many people are actually mistaken by the non-linearity of real world. Many people still believe many real-world problem is linear problem, and sometimes they are mistaken by the non-linearity of real world. So in this picture here, this shows the relationship between income and happiness, and obviously the relationship is non-linear, as we can see here. So sometimes people are mistaken by the non-linearity of the real world. So the SVM is a linear classifier, which means SVM is a straight line like this or like this. And the goal of SVM is to find a straight line which divide different class values, in this case square or circles. Okay. So, but there are actually an infinite number of straight line which can divide these different class values, right? We have this one, this one, this one, this one. We have many straight lines which divide the class values. So then next question is which line we are looking for, which line is better, right? So let's compare these two straight lines, B1 and B2. So which one is better? Intuitively, actually B1 looks better than B2 line. The reason is, let's say, let's talk about this B2 line. Let's say B2 is the SVM line, which divide the different class values. Then let's say we have new data, which is very similar to this data, okay? Then probably that new data is very close to this data, like somewhere around this, right? So this is the new data, which is very similar to this data, right? So this data should be around here, okay? But if you use the B2 line, and this new data is actually the opposite side of this line, okay, which means this new data has different class value than this one, right? That is no good. These two data are very close, very similar, so they are supposed to be the same class values, but if you use B2 line, actually these two data are in opposite side, right? Same thing happens here. Let's say we have a new data which is very similar to this one here, right? And suppose that new data is around here, okay? It's very close to this one. And if you use B2 line, we have same problem. This new data, which is very similar to this data, is actually the opposite side of this line, right? So because this new data is similar to this one, and they are supposed to be the same class value, but if you use B2 line, actually their class values are opposite, right? Different. So these are the problems of B2 line. But on the other hand, if you use B1 line, okay, then if you don't have those problems, right? If you have a new data like this, very similar to this one, both are in the same side, right? And if you have very similar data like this one here, again, these two are on the same side, right? So intuitively, this B1 line is better than B2, right? So now we know that the line B1 is better than line B2. And here in this slide, we're going to explain why this B1 is better than B2 in terms of margin. Okay. So what is margin? The margin is the definition of margin is the following. So let's say we have a line, let's say B1, and then we also have two parallel line with this B1. So this parallel line actually goes through this data, and this parallel line goes through this data. So this data here is the edge of these class values, okay, and it's also closest to this line. And this data is also closest to this this line, and also is the edge of these class values. Okay. So for a given line, we can draw two parallel lines, okay, like this. And the margin of this line, B1, is defined as the gap distance between these two parallel lines. So margin of this line, B1, is actually the distance between these two parallel lines. That's definition of margin, okay? So the margin of line B1 is this, the distance margin between these two parallel lines. And for the case of B2 line, for B2 line, we also have two parallel lines. Okay, and again, this one, the first one, this first parallel line goes through this data, and the second parallel line goes through this data. Okay. So for B2 line, the margin is defined as the distance between these two, B21 and B22. Okay, that's the margin of this line B2. Okay, so if you compare the margin of B1 and the margin of B2, B1 actually has a larger margin than B2. So in SVM, you can say in SVM, when you say a linear classifier is better than the other one, you can say the line with a larger margin is better than the line with smaller margin. Okay, that's the line we are looking for. So actually, the goal of SVM learning is to find a straight line. Okay, find a straight line with maximum margin. Okay, that's the goal of SVM learning. We have learned many machine learning algorithms so far, and actually some of these algorithms are interrelated. And what's happening is, so okay, there is one algorithm, and then that algorithm may have its own problems. Then later on, we have some breakthrough or outside the box thinking. So that algorithm kind of evolve into another algorithm into a different level. Okay, so that's what's happening here. So we have a decision tree. So even though this is very classic algorithm, its performance is not very impressive. So, but later on, by generating many decision trees and by combining them, we have a new algorithm called random forest. So you can say, decision tree kind of has evolved into random forest, and this random forest is quite impressive. It's quite competitive algorithm. Another example is perceptron, and perceptron is linear classifier, and that means it cannot solve non-linear or real-world problems. So because of that, it has evolved into a multi-layer neural net (MLP). Okay, so from the perceptron we add the hidden layer, so it becomes multi-layer, and we use sigmoid function as activation function and use gradient descent. So by using this, perceptron now becomes multi-layer neural net, and the backpropagation is the algorithm to train them. Okay, so now we have a neural net, but neural net has its own problems like a vanishing gradient or too many parameters. So because of that, this performance of neural net is not quite impressive compared to other state-of-the-art method. So recently, we have this neural net has evolved into a deep learning, which we're going to learn later on. And from neural net, we have these. We use deep layers like meaning we add many hidden layers, and we use weight sharing and layer-wise learning and some others. So by using this, this neural net has become has evolved into a deep learning. Okay. So another direction of evolution from perceptron is support vector machine. Okay. And again, perceptron is linear classifier, and because of that, you cannot use this in many real-world applications. In support vector machine is still a linear classifier, but it is able to solve nonlinear problem. It's very interesting. This classifier is linear classifier, but it can solve nonlinear problems. So in support vector machine, it uses maximum margin, and also it uses kernel technique to handle non-linear class, and also it uses optimization techniques. So by using these techniques, perceptron becomes support vector machines. So again, in this slide, we have shown that some algorithms are result of evolution from other algorithms. Like, for example, neural net has evolved from perceptron, and again, support vector machine is another evolution from perceptron. And the chapter here, we're gonna study support vector machine here. So I said the SVM algorithm is looking for a line with a maximum margin. Then why does it look for maximum margin? So maximum margin is good based on our intuition. So line with maximum margin looks much better than the line with a narrow margin. Okay, based on our intuition. Okay, looks good. And also this maximum margin is better based on computational learning theory. So if you need a more theoretical explanation of why this maximum margin is better, then you can take a look at this Voish-dependent lecture. I'm gonna skip here in this chapter. So by the way, if you look at this picture here, this circled data, these data are called support vector. So when you find a line for SVM, actually what matter is these support vectors. These support vectors actually determine the shape of a line, okay? The angle of a line, the everything. Determines everything about the line. Besides the support vectors or other data, it doesn't matter actually, okay? So this actually, in this case, these three support vectors determine the line, SVM line here, okay? So only support vectors matter and the other data are actually ignorable.
So I said SVM is a classifier with the maximum margin. Okay, so in this slide, we're going to define the definition of margin in a mathematical form. Okay, so let's say we have, so this is WX plus B is the line we are looking for. And suppose we have two other parallel line, like WX plus B equals 1 and WX plus B equals minus 1. Suppose we have two parallel data line here. Okay, so in this case, the gap, the margin between these two line, okay, these two line is defined as this. Okay, let's say M is the gap between these two lines. Okay, then M is defined as this. Okay, and from these equations, W x plus minus x minus is 2. So this is 2. So this becomes 2 divided by norm of W. Okay, you may not familiar with this norm. Okay, this norm actually means this. Okay, we call it a second normal form, and the definition is a square root of the sum of square of wi. Okay, so that's the definition of w norm. Okay, so you want to maximize margin. Okay, that's what this SVM does. Okay, then the definition of margin is given as this. Okay, 2 over W norm. Okay, W norm is this. Okay, so that's definition. That's mathematical definition of margin. So we're gonna maximize this M, which is this in SVM. Okay. Finally, you may wonder, okay, in the beginning, I assumed suppose we have line, we have two parallel line, and for each parallel line, the right hand side is 1 or minus 1, okay? So you may wonder, why does it have to be 1 or minus 1? It can be some other number like wx plus b equals c or something like it. Okay, you may wonder okay, right hand side can be any number, right? So actually, you're right. Okay, actually, you can say wx plus b equals c or whatever. Okay, but in this case, suppose wx plus b equals c, then we divide this equation, okay, by c, which is here, right? Then now, if we calculate, you try to find this value, w divided by c and p divided by c, then the problem is same. Okay, it doesn't make difference. Okay, so simply put, you look for line, and we have there are two parallel lines, right? And we can assume these lines, for these lines, the right hand side is 1 or minus 1. Okay, basically we can normalize it, and we can assume the right hand side is always 1 or minus 1. Okay, and this makes our computation much simpler. Okay.
So SVM is linear classifier, and that means SVM can be represented as a linear line. So let's say this is a line the SVM is looking for, wx plus b equals 0. Okay, and what we are looking for is the line with maximum margin. Okay, so this is the line we are looking for, and we have two parallel lines, and these parallel lines go through both vectors like this. Okay, and then for this line, its maximum, its margin should be maximum, right? That's the definition of support vector machine. So the distance between these two parallel lines should be maximum. Okay, M should be maximum. So that's the condition of this line. Actually, there are two other conditions as well. The first condition here says there are many data. Every data here, so every data above this line, this parallel line, its class should be 1. Okay, so every data here should belong to class 1. And every data below this line here, its class should be minus 1. That's another condition. Okay, so in summary, SVM is looking for a line with maximum margin. Okay, and then every data above this parallel line should be class 1, and every data below this parallel line, its class should be minus 1. Okay, that's two other conditions. The previous slide shows two conditions. for the SVM line to satisfy, the first condition was data below this line should be classified as 1, and also the data above this line should be class 1. So these are the two conditions. So if you represent these conditions as a formula, it looks like this. So this means if data is below this line, its class value is -1. And also if data is above this line, this means the data is above this line, then class value should be 1. So we have two formal conditions to satisfy. And actually we can combine these two conditions into one formula, which is given here. So yi times wxi plus b is greater than 1. So it makes sense. If y is 1, then this formula becomes this. And if y is -1, and this whole thing becomes this. Okay. So now these two conditions can be combined into one condition like this. So finally, we have SVM, and SVM is a line with maximum margin, and that maximum margin line should satisfy these conditions. Okay. Now let's summarize the goal of SVM learning. The first one is to find a line which maximizes the margin. That's the first goal. And second goal is to satisfy two conditions we have seen in a previous slide. Actually, these two conditions become one inequality formula in last slide. So these are the formula of these goals. The first goal is maximizing margin. So M is defined as 2 over norm of W. So maximizing this means minimizing this, right? So the first goal is now minimizing this, which is this, okay? And the second condition is there are two conditions, and every class 1 should be above this line, and every class -1 should be below this line. And I said in previous slide, these two conditions can be combined into one inequality like this. So SVM should minimize this one, okay, and also should satisfy these conditions. So finally, in summary, the goal of SVM learning is to minimize this one here. This is equivalent to maximizing margin, okay, and also it should satisfy these inequality conditions, which is given here. So again, the final goal of SVM learning is to minimize this formula, and at the same time should satisfy this formula. That's the goal of SVM learning.
So we have seen the goal of learning in SVM. So we put the goal here again. So we maximize the margin, okay, that means we minimize this. And we also satisfy these conditions. Okay, you remember these are the two conditions are combined into one like this, right? So this is the final goal of SVM. Okay, so this problem is called primal form of SVM or primal problem of SVM. So that is goal. The next question is, how do we solve this problem? Okay, specifically, how do you calculate the W and B value, which minimize this and also satisfies this? So that is the goal. how do you calculate them? Okay, how to solve this problem. When we solve this SVM problem, the technique we use is called constraint optimization method, sometimes called Lagrangian multiplier method. Okay, so we're gonna use this method to solve this problem. Okay, what is constraint optimization method? I'm gonna explain it next slide and a few more. Okay,